Okay, physics. So I wanted to go through two examples of using, I don't know, Newton's second law to calculate something about forces and some of the forces and acceleration. And I want to go through two examples. One is where we have connected boxes, and the other one is where we have stacked boxes, common situations that show up in AP physics classes. So let's see, I'll find some paper. Connected boxes. So this is a classic problem. We're going to have two boxes. They're going to be connected by some sort of string. And then I'm going to apply some force to those boxes. So I'm going to be pulling with some force. I don't know, we'll call this 50 newtons. I'm going to have a box A, maybe it weighs 5 kilograms. The other one weighs 10 kilograms. I'm going to assume this is frictionless for right now. And what I'm curious to find what is the acceleration that this is experiencing. And then secondly, I'd like to know what is the tension that's inside of here. So I'm going to think about this by making three different free body diagrams. One free body diagram for this 5, one for the 10 kilogram box, and then one for my system of the 5 and 10. So let me show you what this looks like. So here we go. So my 5 kilogram is going to be like this. I'm going to have the weight of that pulling down, and I'm going to have the normal force pushing up, and I'm going to have the tension pulling this direction, and I have no friction, so I'm not going to worry about it. These two are going to be equal, so they'll cancel. So the only unbalanced force is in the direction of motion, which should make sense. My 10 kilogram, I'm going to have more going on, so I'm going to have the mass of that times gravity. I'm going to have its normal force, which is different from the other normal force. I'm going to have some applied force, and I'm going to have some tension going into it. So, notice I'm going to apply this force, and some of that force is going to be consumed in accelerating this box, and the rest of that force is going to be transmitted to accelerate this box. Notice, though, these are connected, so these two boxes are going to accelerate at exactly the same rate. So I can make a third diagram which combines those two. So I'm going to say, well, this is my system that I'm interested in, and let's think about that one. So here I'm going to take my whole system of my 5 plus 10, so I'm going to have that mass of the whole 5 plus 10 system, and the normal force, the net normal force acting on those two, so the combined normal force of those two, and those will be equal. I'm going to have some applied force going in this direction, which is going to be going in this direction. And notice that there's no external force going in the opposite direction. So this tension now becomes an internal force. So now we're going to use Newton's second law. So I can use it in any of these three situations and it would be valid. So I can look at the sum of the forces for my whole system, which is going to be sum of the forces. In this case, I'm going to be worried about in the direction of motion. And I'm going to divide that by my total mass. So I need to be careful here. So I can calculate the acceleration. It's going to be my net force. Well, it's only 50 newtons. And what is my net mass is going to be 10 plus 5 is going to be 15. So, oh, good grief, I don't know, what's that, 3.3 or something like that? Meters per second squared. So this is the acceleration that my system's experiencing. So I can now get to tension because, well, I know this equation must be true for any one of these as well. And since I now know acceleration, then I can then figure out the missing force. So I don't know, let's pick the middle one because it's a little bit trickier than the other ones. So why not? So now for the acceleration around block 10, try this acceleration of my system. So acceleration for block 10 now is going to be the sum of the forces acting at block 10 divided by the mass. Again, I'm interested in direction of motion, so the sum of the forces is going to be, what are the sum of the forces going to be? So I'm going to have, well, we'll say this is positive. So this is going to be my applied force minus tension, and I'm divided by the mass of this one, which is going to be the mass of the 10. So I have a value for acceleration and mass, and I have a value for the applied force, so I'm just going to rearrange this. So I can write this as the mass of my 10 times the acceleration of the 10 is going to equal my applied force minus tension, or tension is going to equal my applied force minus the mass of the 10 times the acceleration of the 10. So hopefully this conceptually makes sense, right? So what's my tension going to be? Well, it's going to be that force I put in here, minus how much of that got consumed by accelerating this 10 kilogram block, right? So that's what we're doing here. So it's going to be the amount of force we put in, subtracted from it how much force it took to accelerate that 10 kilogram block. So I'm going to end up with 50 minus, what's 10 times 3.3, or what am I going to get, 17? Just about 17. newtons of force is going to be transmitted. Anyway, so the key thing about this, again, you can't write too many force diagrams, free body diagrams. So this is a good way to think through. I want to think about my system, or I can think about each individual one. And importantly, the connection, you need to recognize that the acceleration is going to be the same between these boxes because they're physically connected. Okay, briefly, let's take a look at stacked boxes. So another common example that we see, stacked boxes. So I'm going to have two boxes that are sitting on top of each other. Let's do the third one, why not? Well, let's just do two and then we'll put it in motion. So, so this is what I'm going to do. I'm going to have these two boxes. I'm going to apply a force. And let's throw in friction here to make it tricky, right? So now I'm going to have friction acting at this contact surface, and I'm going to have friction acting at this contact surface. Let's say we push it hard enough that both of these boxes don't slide with respect to each other. And we can change that, and we will. But I'm going to push this so these two are moving. So here I'm going to have a block box. I don't know, we'll call this 10 newtons, 10 kilograms, and this 5 kilograms, why not? And I'm interested in finding what is the acceleration of this going to be. All right, so let's apply the same 50 newtons. Right? And I'm going to draw three free body diagrams again, but notice I'm going to have something different going on between them. So again, I'm going to have my free body diagram for my 5 kilogram. Here I'm going to have the mass of the 5 times gravity and the normal force coming from my 10 kilogram acting on the 5. As I push it, right, so there's friction there, so something has to be propelling this forward, right, so it's not slipping. So when I push on the 10, the 5 is going to go with it, right, so that thing pushing it forward must be that force of friction of the 10 acting on the 5, right, so 10 on the 5. So that force, something must be propelling it forward. It can't be my applied force, so it must be something acting at the surface there. So, so notice I have unbalanced forces here. This must be causing it to accelerate, right? So I push on these two boxes, and they're both going to accelerate. So now my 10 kilogram box, let's do the same thing. So what's going on? Well, it's going to have its own weight, M10G, right? It also has this thing pushing down on top of it, right? So I've got stacks of boxes, so I've got to take into account both of these weights. M5G is also going to be pulling down on it. I'm applying a force. So this is my applied force. And now what's happening here, right? So the box on top is acting to slow down the box on the bottom, right? So for every bit that this lower box is pushing the top one forward, there's a corresponding force going in the opposite direction here. So remember, this is a contact force. Contact for all forces, but especially contact forces are going to come in pairs. So I'm going to have this opposite force from friction pushing this box backwards. So this is a opposing motion of the box, right? So this is a 5 on 10. Again, I'm going to have a normal force, which is, and I've got one more thing, right? So I've got friction force coming from this contact. I've got the weight of this. I've got the weight of this. I've got the normal force here. But now I have the frictional force from the 10 on the surface there. So there'll be a second frictional force going here. Frictional force of the 10. Right? So the way I want to think about this, at each of these contact points, right, I have my normal force, which is in my vertical direction, and then my frictional force, which is going to be acting at the horizontal direction. And remember, I'm going to have a pair of forces acting at the surface, right? So the floor is going to be pushing this box backwards, and the box is going to be pushing the floor forward. And the same thing is happening, or the opposite thing is happening on top, where my box is going in this direction of motion. And this 5 kilogram, its inertia wants to stay still, right? So it prefers to stay, and the forward prefers to stay stationary. That's going to oppose, the frictional force is going to oppose what it wants to do, and in this case, get it to move. So I could also combine all these together, right? And it gets a little bit easier when I do that. So if I combine all these together, right, then my frictional force becomes internal between the 5 and the 10, right? So, so it's as if I have just a 15 kilogram box, right? So now I'm going to have my whole system, right? I'm going to have my normal force from the floor, right? That's unchanged. I'm going to have M10G and I'm going to have that mass of the M5G. But notice that, yeah, this, yeah, so this other normal force, though, gets added into this one. So we end up having a composite, yeah, normal force. And I'm going to have my applied force, and I just have now the one friction, which is external, right? So this these two are going to cancel, so I have my one external friction. So anyway, so my stacked boxes, I'm going to have two dimensions to worry about when I have friction. So I'm going to have my vertical dimension, which is going to be gravity and my normal force balancing against each other. And then I'm going to have in the horizontal dimension, the direction of motion, I'm going to have my frictional force, and I want to be careful about that, how I assign that. Yep. Anyway, I don't think we're going to solve this outside of saying that I can do the same thing, where I can set up my acceleration in the dimension that I'm interested in by summing the forces in the dimension I'm interested in and dividing it by the mass. So if I'm interested in just the 10 kilogram weight and the acceleration of the 10, I would use the 10 and find the sum of the forces acting on that 10. It's usually easier to start with your system if you can. So the acceleration of my system. Acceleration of my system, what's that going to be? That's going to be the sum of my forces acting horizontally on my system divided by the mass of my system. Now, some of the forces acting horizontally on my system, well, I'm going to have my applied force. Right, so I'll make this positive direction. I'm going to have applied force, and I'm going to have friction force going in the opposite direction. So if it's in motion, this is going to be kinetic friction. So I'm going to have my coefficient, my frictional force is equal to the coefficient of kinetic friction times the normal force, and divide this by mg of my system, mass my system times gravity. And all these things I know, right? So I could find the coefficient of, well, if I knew the coefficient, I could find acceleration. If I know acceleration, I can find the coefficient. Yeah. So anyway, stacked boxes, they get a little bit tricky, but again, the key to it is think about the vertical and horizontal dimensions. And yeah, it should make sense from there. Hope that helps. Bye.